Hello, myself Vishal Sandeep Thakur is going to present a topic on heat energy storage with the help of thermochemical materials. It was presented by me, my friend Harsh Amrish Kumar Nakum and Shivam Parmar under the guidance and supervision of Dr. Mahaburi and under the course Project Part B. The table of content is listed here. Initially, we started with the introduction of thermal energy storage, its classification, application, and then why we selected calcium hydroxide, what is the working principle of it, the existing drawbacks in solution of calcium hydroxides, basic reactions involved in thermochemical, the assumptions which we took on a multiphysics model, parameters, material properties, model descriptions, and the design and result and discussion of this project was done, and at the end conclusion was given. Talking about thermal energy storage, it is a system that can store heat or cold to be used later at different conditions such as temperature, place or power. Here in figure 1 shows a basic representation of heat energy storage system. Here storage, chiller, building load, expansion device and pumps are shown, and the excess energy, or we can say the surplus energy, is stored in the storage. Thermal energy storage is a system which stores surplus energy or heat. It is further divided into three parts, that is sensible heat storage, latent heat storage and chemical energy storage. In sensible heat storage, the heat is stored in the form of solids and liquids. In latent heat storage, it is stored in the form of solid liquid, liquid gaseous or solid solid. And the main focus of our topic is chemical energy storage, in which chemical reactions take place to store surplus energy. Figure 3 shows the high temperature thermochemical energy storage is further divided into solid gas reaction and gas-gas reaction. Our main focus here is on solid gas reaction, as in project part A we discussed various importance of solid gas reactions and we finalized this type of reaction, under which we finalized two materials which were cobalt oxide and calcium hydroxide. Now in this project part B we are moving ahead with calcium hydroxides, and we have listed that why we choose this type of material. It is very important, before moving ahead we should discuss what are the applications of thermochemical energy storage. As per the research, we have found that there are four types of applications which are widely used. Those are waste heat recovery, solar thermal power plant, thermal energy transportation, and for solid oxide fuel cells, which is the future technology. Thermochemical reactions are reversible in nature, with the thermal energy being supplied and released during the endothermic and exothermic steps respectively. Here in the operation of TCES involves three significant steps. Those are charging, storage and discharging. As shown in figure 5, when an energy is given to a reactant AB in the form of heat, the excess heat is stored in the form of products such as A and B. Now, as per the application, when we want to reuse that excess energy or heat, we can simply supply heat and discharge it in the form of reactant. Calcium hydroxide, traditionally called slaked lime, is an inorganic compound with the chemical formula CaOH2. It is colorless crystal or white powder and is produced when quicklime is mixed or slaked with water. Calcium hydroxide is produced commercially by treating lime with water, as shown in the reaction below. Here in figure 6, structural representation of calcium hydroxide is shown. Now the question is why we selected calcium hydroxide instead of other materials. So calcium hydroxide offers various advantages, such as it is cheap industrial mass product and abundantly available worldwide. Secondly, the reaction enthalpy is high, leading to high possible energy storage densities. Also, the charging and discharging temperature of the reaction can theoretically be adapted in a wide range of approximately 300 to 650 degrees Celsius. The applications of system could potentially be beneficial for many high temperature processes such as storage and utilization of industrial waste heat, or as an alternative storage solution in future concentrated solar power plants. Now the working principle of calcium hydroxide is shown, in which the formation of calcium hydroxide is there. Calcium hydroxide is heated during dehydration and breaks down into calcium oxide and water vapor. This type of reaction is called endothermic reaction and the process is called charging process. Now when a reaction is exothermic, heat is produced when water is heated to steam. which then interacts with calcium oxide to make calcium hydroxide and release heat. This type of reaction is called exothermic reaction and a process is called discharging. Before concluding the information on calcium hydroxide, we also need to know the existing drawbacks and solutions of it. As can be seen in figure 8, the drawbacks are high decomposition temperature, which can be solved by doping of iron with calcium oxide. The second drawback is low thermal conductivity, which can be easily solved by the design and composites. The formation of agglomeration and cracks can be uh, eliminated with the help of composites. The formation of carbon dioxide and the affection of it can be minimized with the help of filters. As can be seen, there are three types of solid gas reactors. The first is fixed bed reactor, second is fluidized bed reactor, and third is moving bed reactor. Now, as per the research done in project part A, we finalized fixed bed reactor, and there are two types of fixed bed reactor. First is direct contact type and another is indirect contact type. Our research is more focused toward direct contact type, and assumptions for a multi-physics model of our project is illustrated in the upcoming slide.
So the next slide is about all the assumptions we took for our multiphysics model. The first one is that throughout the hydration process, the gas is handled as an ideal gas. The second one is the solid porosity and the particle diameter of porous medium, which is thought of as a continuous medium, stay unalerted during the hydration process. Since the temperature of solid phase and the gas phase are equal during the hydration process, the local thermal equilibrium is valid for thermal transmission in porous media. The hydration procedure does not take into account radiation heat exchange. The second last is the link between equilibrium temperature and the vapor pressure meet as a reaction's equilibrium temperature varies with pressure. And the last one is we are neglecting the heat resistance between the fins, the sidewall and the bed. So now moving further ahead, the next slide is about all the parameters which we took in our multiphysics model. The first table shows that the initial and the boundary conditions. So as we can see in the table that all the parameters of initial and boundary conditions are mentioned in it. So the pre-bed is 2 into 10 raised to 5 and the initial temperature is 350 degrees Celsius, and the second table shows the values of pre-exponential factor, activation energy, reaction enthalpy, density of calcium oxide and hydroxide, and other thermodynamic terms. And all the terms which we took in our multiphysics model is mentioned in this table. So now let's jump on to the next slide, which is about the material properties. So as we all know that selecting the best material for the thermochemical heat energy storage is a very important factor, and in our thermochemical heat energy storage we chose calcium oxide. So table 3 shows the material properties of calcium oxide. So as we can see in this table that the molar mass of water, calcium hydroxide and calcium oxide is 0.018153 kg per mole, then 0.074093 kg per mole, and then 0.056077 kg per mole, and all the properties are mentioned in this table. The next table is about the material properties of copper, because our fin is made up of copper, and as we can see in this table that the heat capacity of constant pressure, the which is Cp value is 385 and the reference temperature is 298 Kelvin. So the next slide is about the model description. This table gives us information about all the parameters of our selected model, that the what width we took and what height and everything. So the width of the reaction bed is 0.02 meter, the height of the reaction bed is 1 meter, the width of fin is 1 centimeter, the length of fin is 0.2 centimeter, the pressure of heat transfer fluid is 1 bar, the starting temperature and starting temperature is 350 degrees Celsius. The volume flow through the reactor is 18.75 meter cube per hour, and the inlet and the starting temperature of the HDF is 350 degrees Celsius.
As can be seen in the figure, the design of calcium oxide reactor bed was done. A 2D axisymmetry model was created with the help of COMSOL multiphysics, in which three models of reactor were made. First, with no rectangular fins was made and analyzed by Vishal Thakur. Second with 50 number of fins was done by Harsh Nakum, and third with 100 fins was made and done by Shivam Parmar. The reaction which was made into focus was charging or say hydration process, in which calcium oxide is there on the reactor bed and high temperature steam strikes on it from the top, which results in the formation of calcium hydroxide, and heat is dissipated in the atmosphere. Four thermocouples were attached to sense the temperature at the top, bottom and middle part of the model. Now to get heat transfer with a faster rate, addition of fins were made. Future result and analysis depicts the outcome of the simulation done by us.
We will now discuss about the results. The density versus time relationship for the reactor with no fin is shown in the first graph. As previously discussed, as heat dissipation increases, the exothermic reaction rate increases. Because the heat dissipation is not uniform over the length of the reactor, the time required to complete the exothermic process varies. As seen in the graph, the reaction rate at point T11 is quicker than at points T1, T5 and T15. Because the heat dissipation is lowest at point T15, the reaction time is the longest. The density versus time relationship for the reactor with 50 fins and 100 fins is shown in the figures at the bottom. After adding the copper fins, the reactor's surface area and heat dissipation increases. This reduces the time required to complete the exothermic process. Heat dissipation is maximum at the center of the reactor, which is why the exothermic reaction process is completed early at point T11. The next slide will discuss the time taken at all four locations in all the three reactors. In the table below, we can see the time taken to complete the exothermic hydration process at all 4 points in the reactor with no fins, 50 fins and 100 fins. As shown in the table, the reaction completes first at point T11, which is in the center of the reactor, then at points T1, T5 and finally at point T15. Compared to the reactor without fins, the reaction time reduces by 2 minutes after adding 50 fins, and the reaction time reduces by 6 minutes after adding 100 fins. The temperature versus time relationship for the reactor with no fins is shown in the first graph below. The starting temperature is 350 degrees Celsius. The temperature in the reactor rapidly rises after the water vapor is introduced. The temperature of bed rises from 350 degrees Celsius to 480 degrees Celsius in the first 5 minutes of the reaction. The temperature then reaches its peak of 500 degrees Celsius in all the three reactors at nearly 12 minutes. The reaction bed temperature then decreases and returns to its initial temperature of 350 degrees Celsius after 205 minutes in all the three reactors. The below table shows the maximum temperature reached at 4 points in all three reactors. As we can see in the table, in the reactor without fin, the maximum temperature reached is 504.90 degrees Celsius, while in the reactor with 50 fins, the maximum temperature reached is 504.85 degrees Celsius, and in the reactor with 100 fins, the maximum temperature reached is 504.74 degrees Celsius. We can see the temperature reduction in the reactor after adding the copper fins, but the reduction is not significant.
To conclude the research project, it was seen that heat dissipation was increased, the time was variable to complete an exothermic process, reaction time at point T11 was the quickest among all, reaction time was longest in T15, copper fins increased the distribution of heat, and the analysis showed that comparison to the reactor without fins, the reaction time reduced by 2 minutes after addition of 50 fins and by 6 minutes after addition of 100 fins. We can also see the temperature reduction in the reactor after adding the copper fins, but the reduction is insignificant.